In this video we're going to start looking at line integrals. Now, just to recap, the question that we've asked, and it's been a theme throughout the previous videos, is that given some random charge distribution, how can we find the electric field? So we did come up with Gauss's law, which tells us the flux of the field over a surface is equal to the total charge divided by epsilon naught. And then we were able, through the idea of divergence, the divergence theorem, to write that in this form here. So it's the differential form of Gauss's law. So it tells us that del dot E is equal to rho upon epsilon naught. So rho is the charge per unit volume. So we were started off with one equation and an infinite number of unknowns, and we progressed to one equation in three unknowns. But we're still in the process of trying to work out where do we go from this point here with one equation and three unknowns. So that's the direction that we're going to take at the moment, and that's going to introduce us to ideas of line integrals and curl. So first of all, we're going to look at the idea of work. Okay, so in work in physics is defined as the work done is equal to the force times a distance. So if you apply a force to an object, there's a little man here, option 1 here, a little man applies a force F to this object here and it moves a distance d. So then you could draw down a little graph and you can say, well, there's the distance d, it's moved along the axis here, and that's a force that you've applied. So if we are applying a constant force here, so the force doesn't change, it doesn't wave up and down, it's just a constant force, then we can say the work done is going to be the area under this graph. Is going to be our force times our distance. But as you well know, when you go to push some things, you maybe get a little bit tired and you don't apply the same force all the way through the push. So again, we're pushing it with a force F over a distance, but this time here the force F is variable. So we're still looking at the area under this graph here will give us the work. But the area now, instead of force times distance, is going to be the integral of this function of x times dx, okay, where x is the distance moved. Now, it's not just as simple as that though, because we know that if we were looking at above, say here, and we're applying a force to try and push a car, then if we are applying a force from the side, but the car doesn't move in this direction, it'll move in that direction there. Now the only force that we say that does work is a force that is applied in the direction of the movement of travel. Okay, so that's the direction of movement of travel there. So the only component of this force here that actually does work is a component in that direction. Now the component in that direction, you can see if you say F1 upon F is going to be the cos of this angle. So it means that F1 is equal to F cos this angle theta. Okay, so whenever we write down our force equations, it's not actually force times distance, it's going to be F times d cos theta. So we can write this out again, rather than as f d cos theta, we can write it out as f dot d, so we can use the dot product. Now if you're unsure about the dot product, there's a little video up here and you can have a little look at that video and that will explain what the dot product is. But that's not going to tell us the whole story, because what if we really generalize it and we have just a three-dimensional space, so it's just an x, y and z coordinates, and you can take the components as an I, j and k. And let's say we push an object and it moves in space, and it moves in just a three-dimensional sense, so that is, imagine that as travelling through space in some random direction. Then the work done is, previously we've seen if it was a variable force, it would be the integral f of x dx. But what if it was a variable force and it was applied and we moved over some variable direction? Well then what we could look at is, rather than it be f dot d, we'll be looking at it would be the only component of the force that does work would be in the direction of movement. So I've drawn a few spots on this curve here. So the direction of movement at each point is going to be the tangent at that point. So at that point there, the direction of movement is in this direction, and the direction of movement here is in that direction. The direction of movement is there, the direction of movement is up there. So we need to find then the tangential direction, the tangential component for all the points along this surface, so that we can then form, instead of F dot D, it's going to be our force, and it's dotted with the tangential direction, and of course the D is just the ds, which is, the ds now is a small element along this curve. Okay, so that becomes our equation for our work. It's the normal component of the force in the direction of movement over the small surface, small direction element ds. Okay, the magnitude of this small element of curve ds. So that's what we're looking for, but we know that this force, well, we've written out forces before, we've written out functions before that are vector functions, so we can split that up into its component parts. So the component parts are going to have a force in the x direction, which is given by I, which is a function of x, y and z, and the same for y in the j direction, and the same for k and z in the k direction. Okay, so we've seen that before, and we've dealt with that in one of the very first videos. But what we're interested in is finding this value t, which is the unit tangent to this curve. So how do we find that? Well, let's imagine we draw a little section of the curve there in yellow, and we take a couple of points in the curve, say we call that point S, and then we've got another point in the curve here, it's going to be S plus delta S. Okay, so what we do is we imagine the curve as being parameterized with respect to the arc lengths. Okay, so what we're saying is the position of a point on this curve is given by the x component, which will be some function x of s, and y is y of s, and z is z of s. So what we're really saying is that this, if we take this infinitesimal length here s, then this infinitesimal length here s will actually give us the function that will tell us the x coordinate, and the function that will tell us the y coordinate, and the function that will tell us the z coordinate. Okay, so we're parameterizing this curve with respect to its arc length. So then we can say that the point s plus delta s is going to be x of s plus delta s, y of s plus delta s, and z of s plus delta s. So we could draw a little arc joining, so that's just a straight line, so we can draw that little line from s to s plus delta s. We'll call that delta r. So that delta r, that's just a vector sitting in space, so that vector can be written as I delta x plus j delta y plus k delta z. Okay, it's just a simple vector. So then what we can do, and you can see this up here using a wee bit of thought, if we let this value delta s tend towards 0, then that delta r, you can see by simple differentiation, is going to tend towards the tangent at that point. So we'll just do that. So we're looking at delta r upon delta s. Well, delta r is what we have above, divided out by delta s, we have this here. And then if we take the limit as s tends towards 0 of delta r upon delta s, we get this here, I dx by ds plus I dy ds plus k dz by ds. And we can see then that that there is going to be the tangent. But we can note as well is that as delta s tends towards 0, then the magnitude of delta r, so as this delta s tends towards 0, then the length of this delta r, well, it'll tend towards the length of that little arc delta s. So it means that if we take that limit as delta s tends to 0 of delta r upon delta s, well, this one just tends towards that value, so they tend towards the same value. So we're just going to get the limit will tend towards 1, so it's just like dividing two numbers together with the same number, so you'll just get a value of 1. So it means that not only does this equation here give you the tangent, it actually gives you the unit tangent. Okay, so that's us found our unit tangent t. So the unit tangent t can be written as I dx ds plus j dy ds plus k dz ds. So that is our unit tangent. So we can put this here back into our equation up here, and you can see that what you're going to get is, when we put that into that equation up here, we're going to get our f, sorry, I'll come back up again, we're going to get our vector function f, okay, that has got components I, j and k, and we're going to have a vector function t that's got components I, j and k. So of course whenever the I multiplies with the I, we'll get a value of 1, but when the I multiplies with j, we'll get 0, and when the I multiplies with k, we'll get a 0. So we'll only get one component for each of these whenever we multiply them out. So I've not written it out in full, but you can see then, if we have our vector function here, and we take the dot product of the vector function with this function here, then when we dot the I here with the I in this here, we get a value, but when we dot the I in here with the j, we get a 0. We dot the I with a k in here, we get 0. The same for this, we'll only be left with the j component, and the same with this, we'll only be left with the k component. So we'll simply be left with the function, but only the x component of the function, and the function, the y component of the function, and only the z component of the function, times our dx, times our dy, and times our dz. So that there is the final value that we're looking for, the equation we're looking for, that defines the work done over some path. Okay, so that's the end of really the derivation there, and that's all the derivation. So we'll go on and we'll look at simple examples. This is the example that's straight out of the book, so I'll just talk our way through. So we've got, let's say we've got a closed path here, so we travel along C1 up C2 and down C3. So we've got some vector function there that's defined in this space, and it's a function of x, y and z. It's such that it equals I, y minus jx. So we know we're looking to find the work done in moving round this loop. So the work done, from what we've seen before, is going to be the normal component of this vector function. Sorry, it's going to be the vector function. It's going to be the dot product of that with the tangential component added up over each small element ds. So we can write that as per the bottom of the last page there is the integral of y times, and you can see this now if I go back onto the last page so you can remind you it. So we can see it's going to be f of x dx, f of y dy. Okay, so let's go back in there. So it would be f of x dx. Well, f of x in terms of dx is just our y component. Okay, so that's our y component, that's in the direction of I, okay, which is related to our dx, which is going to be the value of y, and then the f of y dy. Okay, well the f of y component, well the y component is just the factor of minus x here. Okay, so we're going to have a y dx minus x dy. So we go around our three paths, C1, C2 and C3. So we notice in path C1 that, well, the y equals 0 and dy equals 0. So it means when we do this integral, we're going to have our y is 0 there, so that term's 0, and we've got our dy is 0, so that term's 0, the whole thing's 0. And then when you go in and look at path C3, then we know in path C3 our x is equal to 0 and our dx is equal to 0 along that path. So we can see the integral of y will and the dx equals 0 there, so that disappears. And this section here, our x equals 0, so that disappears, so that whole thing is equal to 0. So the only thing that adds any work is going to be along path C2, and we got to work out the parametric equations for that path C2, and here they're done here. If we write that point there as 0.1, so we can see a distance along here to that point there is going to be 1 minus x. Okay, that's our x there, that's our y. So it's going to be 1 minus x. So you can see 1 minus x upon s. Okay, so s is the distance up here, is equal to the cos of 45 degrees, which is 1 upon root 2. And you can also say that y upon s, this distance here, is going to be our sine of 45 degrees, which is also 1 upon root 2. So then we can rewrite that as, and transpose that for x. So x is 1 upon s, 1 minus s upon root 2. And if we differentiate that, you just get minus 1 upon root 2. And we can transpose this for y. So y equals s upon root 2. We differentiate it, you get 1 upon root 2. Then what we want to do is we've got to work out our integral up here. So y dx minus x dy. Okay, so we just pop our values in. So we're going to have our value here of s upon root 2 for our y, and our dx is going to be our minus 1 upon root 2 minus the value 1 minus s upon root 2, which is our x, times our dy, which is going to be our 1 upon root 2. So we work that out, and we'll get our, take a common factor, minus 1 upon root 2 out, the integral 0 to root 2, and we get our value, work through that, we'll eventually get our value equaling minus 1. So the work done is minus 1. Okay, and the only direction the work is getting done is in this direction here, so there's no work done in this direction or in this direction, so it's only that one part of the path. So that's all there is for this video. Next video we'll go on and do a little example on path independence, and then we'll move on to the idea of curl. Okay, so thank you for listening, and goodbye.